Assalamu alaikum. Welcome to the class. This is lecture 1 for week 1 for the course Microprocessor Programming and Interfacing. Course code is C. Before we start covering contents of this lecture, a brief review of the previous week. Up till now, we have discussed pin diagram of 8086 and 8088 microprocessors. We have discussed minimum mode pins and maximum mode pins, and we have discussed fully buffered 8088 and 8086 microprocessors, and in connection with the pin functions we have discussed bus cycle of microprocessors and states of microprocessors. So in this lecture we are going to discuss internal architecture of 8088 8086 microprocessors. Both of these microprocessors may be studied by dividing it into two logical units. First one is called execution unit and second one is called bus interface unit. So there are two logical parts. First one is execution unit. Execution unit tells the bus interface unit from to fetch data. Data may be of two types. Decodable data means instructions, or simple data, non-decodable data. Second task of execution unit is to decode instructions fetched from memory and identify which operation is to be performed by microprocessor. Then after identification of instruction, that instruction is executed. That is the purpose of execution unit. Then second logical part is bus interface unit. Bus interface unit sends addresses on address bus. That address may belong to memory. So from memory, bus interface unit will be bringing instructions through data bus. Or the generated address may be of any input device. So it may receive data from any input port or input device, or the address generated by processor may be of any output device. So bus interface unit will be writing data through data bus to that output port. Same is the case for memory. Some simple data, non-decodable data may be read from memory through bus interface unit, or some data may be written to memory by using bus interface unit. As the name shows that execution unit is responsible for execution of instructions. So for identifying the instruction fetched from memory, there is an instruction decoder which identifies which instruction is fetched from memory. So instruction decoder translates the operation codes, or you may say instruction, into a series of actions which to be carried out by the execution unit to completely execute that instruction. Or you may say that a macro operation will be completed by following a series of micro operations by execution unit after decoding that instruction. So control circuitry will be required to use the different units of the execution unit. For example, if you are having a move instruction and you have to move some data from one register to another, you will be requiring some control signals to transfer that data. Or otherwise, if you are having an add instruction, then some other control signals will be involved. You will be using ALU, and you will be using temporary registers during the add operation, and the result of the add operation will be stored somewhere. So you will be having some control signals for storing that result to the destination. So there will be control circuitry within execution unit. The other unit present in execution unit is arithmetic logic unit, ALU. 8086 processors are having 16-bit ALU in its ALU execution units. So ALU is responsible for performing arithmetic and logic operations like add, subtract, and, or, XOR, increment, decrement, complement, and shift and rotate operations. So all of these arithmetic and logic operations are performed within ALU, and ALU defines that the processor 8088 and 8086 are of 16-bit because at one time you may manipulate 16-bit data. So that is the reason why we declare both of these processors as 16-bit processors. The last part of the execution unit is internal registers. So in the next slide we are going to discuss internal registers. What are these internal registers present in execution unit? So in this slide we are having a list of registers. These registers are called general purpose registers. All of these general purpose registers are of 16-bit each, and all the general purpose registers are multi-purpose registers. Multi-purpose means these registers may be used for holding data within move, add, subtract, and or instructions. First four registers are AX, BX, CX, GX. These four registers may be further divided into 8-bit parts. As you may see here that AX is divided into 8-bit parts: AL lower 8-bit, AH higher 8-bit. BX is divided into BLBH. CX is divided in CLCH, and DX is divided into DLDH. So we have assigned a label for 8-bit parts, and these 8-bit registers may be used as independent registers also. So we start with AX register. AX is called accumulator register, and it is multi-purpose register, and the dedicated operation assigned to this register is within string instructions, isolated IO instructions, and multiplication division instructions, and some other instructions are also there. We will be discussing this register with when we will be discussing instruction set in detail. Then BX register, base index register, it is also another multi-purpose register, and the dedicated operation assigned to that register is when you are using this register to access memory. Whenever you are using this register to access memory, it will be holding offset address within data segment. What is the offset address? That will be discussed in the coming lectures. Now CX register is called count register, It is another multipurpose register and it holds count for some instructions like loop, shift rotate instructions. Detail will be coming in instruction set topic. Then DX register is called data register. In addition to the multipurpose operation, DX is used within isolated IO instructions and multiplication division instructions. So we'll be discussing this register also within instruction set topic. Then there is SI register, source index. It is also another multipurpose register, and the dedicated operation for this register is within string data transfer instructions, and within string instructions this register will be holding offset address within the data segment, and that will be the source address. DI register is called destination index. In addition to the multipurpose operation, this DI register is used within string data transfer instructions for holding offset address within access segment, and that address will be our destination address. Then base pointer register, BP. It is also another multipurpose register, so it may be used within move, add, subtract, and or shift rotate instructions for holding data. In addition to the multipurpose operation, if you are going to use BP to access memory, then this register will be holding offset address of stack segment. Detail will be coming within real mode operation coming in the next lecture. Then stack pointer SP register. It is also another multi-purpose register, but dedicated operation assigned to that register is when you are using stack operation instructions, push and pop instructions. So during stack operation instructions, this register will be holding the stack offset address. In this slide, we are having a list of registers. These registers are also of 16-bit, and these registers are called special purpose registers. The first one is IP, instruction pointer. Instruction pointer holds the offset address of instructions within code segment. As within code segment, we will be having instructions. So the offset address will be within IP. Detail will be coming when we will be discussing the real mode memory addressing topic. Then the second register here is flag register. It is also of 16-bit, and this register will be holding flag bits. Flag is basically a flip-flop that may change its logic label. It may have logic 0 or logic 1 in it, and there are two types of flags, status and control flags. So detail will be coming in the next slide. Then there are four segment registers: CS code segment, DS data segment, SS stack segment, and ES extra segment. When we are going to discuss memory access of 8088 and 8086 processors. So there are four segments possible in memory, and those segments are called code segment, data segment, stack segment, and access segment. So these four registers are for holding the base addresses of these four segments within memory. So CS will be holding the base address for code segment in memory, DS will be holding the base address for data segment in memory, stack segment will be holding the base address for stack segment within memory, and access segment will be used for holding base address of access segment in memory. And all these registers are of 16-bit for 808 microprocessor and 806 microprocessor, and in the advanced versions also. In this slide we have to discuss flag register in detail. So you may see the 16-bit pattern of flag register here in this slide. If we start from the LSB, first bit is C, then you are having U, P, U, A, U, Z, S, T, I, D, O, U, 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 U. So U bits are undefined bits. No operation is assigned by Intel to these bits, U bits. Remaining 9 bits are having active flags. As we have discussed earlier, that flag is a flip-flop. It may hold a 0 or 1 depending upon the generated condition. So these flags bits are divided further into two categories: status flags and control flags. 6 status flags are listed here and 3 control flags are listed here. So first status flag is carry flag. Whenever during an addition operation you are having a carry from MSB, carry flag will be having logic 1. Or if you are performing subtraction operation using microprocessor and you have taken borrow on the MSB of the number, then carry flag will be having logic 1. Otherwise, if there is no carry in case of addition or no borrow in case of subtraction on an MSB, then carry flag will be having 0. Then second status flag is parity flag. Parity flag shows that how many number of ones are there in the result. If number of ones are an even number, then parity flag will be having logic 1. Or otherwise, if you are having odd number of ones in the result, then parity flag will be having logic 0. Then auxiliary carry flag. Auxiliary carry flag shows that if there is a carry generated from bit number 3 to 4 when you have performed an addition. In case of subtraction, if you have taken borrow from bit number 4 to 3, then auxiliary carry flag will be having 1. Otherwise, if there is no carry generated from bit number 3 to 4 in case of addition, or if you have not taken borrow from bit number 4 to 3 during subtraction, then auxiliary carry will be having logic 0. Then 0 flag. If after some data manipulation instruction result is generated having all 0 bits, then 0 flag will be having logic 1. Or otherwise, if you are having some non-zero result after some data manipulation instruction, then 0 flag will be having logic 0. Then S flag, sign flag. If the generated result is of positive sign, then sign flag will be having logic 0, and if the sign of the result is negative, sign flag will be having logic 1. Positive result mean the MSB of the result will be 0. Negative result means you will be having a resultant number having MSB 1. Now the last status flag is overflow flag. Overflow means in case of addition, if you have added two positive sign numbers, and you are getting a negative sign number as result, then an overflow is generated. Or in case of the second case is if you have added two negative sign numbers and you are having a positive result, that is also another overflow condition. So overflow flag will be having 1. Otherwise, if there is no overflow flag will be having logic 0. In case of subtraction, if you have subtracted positive number from negative number and you are having a positive sign number as a result, that is an overflow condition. And if you have subtracted negative sign number from a positive sign number and you are having negative sign result, then overflow is generated. So overflow flag will be having logic 1. Otherwise, overflow flag will be having logic 0. There are three control flags. First one is the trap flag. Second one is interrupt flag. And third one is direction flag. The detail is coming in the coming slides. In this slide, you are having an example for status flags. So we have added two numbers. First number is 4068 hex. Second number is 72A9 hex. And result is B311. So after performing this addition operation, microprocessor will be having this condition within status flags. Carry flag will be at 0 as no carry is generated from the MSB. Parity flag will be at logic 0 as there are 7 number of ones in the result and 7 is an odd number. Auxiliary carry flag will be having logic 1 because you may see that from bit number 3 a carry is generated to bit number 4. And as you may see that the result is B311 and that is a non-zero result, so 0 flag will be having 0. Sign flag will be having logic 1 as the result is having MSB 1. And overflow flag will be having 1 because we have added here two positive sign numbers. MSBs are zeros for the numbers 4068 and 72A9, but in resultant number you are having sign bit 1, so there is overflow generated within this calculation. In this slide we are having another example of status flags, how status flags will be affected after an arithmetic operation. So we have an example of subtraction here, 8-bit subtraction operation. So we are having 68 first number and another number A9 is subtracted from 68 hex. So result is BF hex after subtraction, and now you may see that for performing this calculation you require a borrow at MSB. So carry flag is having 1. Then after performing calculation, BF is having 7 number of ones in it. That is an odd number an odd number of ones. So parity flag will be 0. Auxiliary carry flag is also 1 because you may see that there is a borrow taken from bit number 4 to 3. So auxiliary carry flag is also 1, and BF is a non-zero result, so 0 flag is having logic 0. Sign flag is having 1 as the result is having MSB 1. So a negative result is generated. Sign flag is having 1. Now overflow flag, we have subtracted a negative number from a positive number, and result is having a sign bit of the second number, that is 1. So this is an overflow condition. So you have subtracted negative from positive and result is negative. So that is an overflow condition. So overflow flag will be having logic 1. In this slide we are having control flags. So first control flag discussed here is interrupt flag. Interrupt flag may be assigned logic 0 by using an instruction, that is CLI, clear interrupt flag. Interrupt flag may be assigned logic 1 by using an instruction called STI, set interrupt flag. So these instructions will be discussed within instruction set topic. So if you have assigned logic 0 to interrupt flag, interrupt request pin discussed earlier will be disabled. Or if you have assigned logic 1 to interrupt flag, interrupt request pin will be enabled as we have discussed earlier. Second control flag is direction flag. We have discussed that there are two registers SI and DI, and those registers holds the offset address within data and access segments during string data transfer instructions. So in case of string data transfer instructions, direction flag may be used to automatically increment or decrement these two registers. Detail will be discussed when we will be discussing string data transfer instructions within instruction set topic. Up till now, you should know that direction flag may be assigned logic 0 by using CLD instruction, and direction flag may be assigned logic 1 by using STD instruction. Now the last control flag is trap flag. Trap flag is used by some softwares. No instructions are provided for user to assign logic 0 and 1 to trap flag. But some softwares are available like debug, utility of DOS, that may assign logic 0 and 1 to trap flag for enabling and disabling single stepping. If trap flag is having 0, then single stepping is disabled, or otherwise if trap flag is having logic 1, stepping is enabled and you may debug your code. For discussion of direction flag, we have taken an example of move SB instruction. MOVSB string stands for move string byte instruction. In this instruction, a byte is to be copied from data segment into access segment. The offset address of data segment is present within source index register, SI register, and offset within access segment is present into DI register, destination index register. So figure is shown here. The source physical address is DS into 10H plus SI. From here you have to read a byte into microprocessor in the first cycle. Then in the second cycle that byte will be written to ES into 10H plus DI within access segment. So that is the complete transfer. But string instructions are not used to transfer only one byte, but you will be copying a block of data from data segment into access segment. So your block of data will be having a top address and the bottom address. So if you are going to start transferring data from the bottom address, then you have to place direction flag as 0. So after each byte transfer, DI and SI will be incrementing by 1, and you don't have to increment DI and SI manually, but that will be an automatic increment. Or otherwise, if you have started transferring data from the top address of your block, then you have to place DI equal to 1, and after each data transfer, offset addresses in SI and DI will be decrementing by 1 automatically. So your block will be expanding downward, and that is the basic discussion for direction flag. More string instructions will be discussed later in instruction set topic, and more discussion will be coming regarding direction flag at that point. In this slide we are having the components present within bus interface unit. First one is the physical address generator. So by using a physical address generator, microprocessor will be generating 20-bit address, and for generating physical address it will be requiring segment registers for base addresses and offset addresses. So after calculation of 20-bit address, that address will be placed on 20-bit address bus, and all the buses, address bus, data bus and control bus will be under the control of bus interface unit. To control the operations on buses, some bus control logic will be present within bus interface unit, and BIU will be assisting EU for placing addresses on address bus and to receive instructions and data from memory, or to transmit data to memory or IO. The last unit present within BIU is instruction queue. Instruction queue is basically a shift register, first in first out shift register. In case of 8088 processor, there is a 4-byte instruction queue or shift register. In case of 8086 microprocessor, there is a shift register of 6 bytes. This instruction queue is for storing prefetched instructions from memory. Whenever EU is decoding an instruction or executing an instruction within the same time, BIU will go to memory and will be fetching instruction bytes from memory and those instructions bytes will be stored in the instruction queue. When EU will be free for execution of next instruction, it will not be requiring to go to memory for picking of next instruction, but next instruction will be picked from instruction queue present within bus interface unit of microprocessor. So this operation will be called pipelining, and by using pipelining, some parallelism is introduced within 808 and 806 microprocessors. So it will decrease the execution time of instructions. And we have discussed earlier the Q status signals QS0 and QS1 during the topic of hardware specification. So those control signals was showing the status of the Q. Now we have to discuss a block diagram for internal architecture of 808 806 microprocessors. So in this slide you are having a block diagram for 806 microprocessor. So you may see that there is a dotted line separating the two logical parts of 808 806 microprocessor. Left side is for execution unit and right side is for bus interface unit. So in execution unit you are having control system. Control system will be having instruction decoder as well as control circuitry, and it will be using ALU, internal registers, flag register and temporary register uh, whenever they are required for execution of the instructions. So on the right side you are having bus interface unit. On the top of bus interface unit you are having a summer, that is physical address summer or adder. It will be using segment registers as well as offset addresses to generate 20-bit address, and that address will be placed on address bus, and data will be coming from memory and uh, will be provided to instruction queue. You may see that here we are discussing 8086 microprocessor, so instruction queue is of 6 bytes. Whenever execution unit is free to execute next instruction, it will be picking next instruction from instruction queue. So there is no need to visit memory for picking the next instruction, but next instruction will be provided from instruction queue.